Just 1 second. Okay, we are now live on YouTube. So welcome everyone to this virtual conference called New Technologies for Resilient Infrastructures. My name is Margarita Skachenko. I am the International Cooperation Coordinator at the Faculty of Engineering of the University of Santiago in Chile. And this conference is organized in the frame of our International School of Perspective on Seismic Hazard Analysis and Disaster Risk Management, organized by the Faculty of Engineering of the University of Santiago de Chile. And in this instance, we are very happy to count with the participation of Aníbal Graterol Lomelly, Technical Coordinator at the Engineering Simulation and Scientific Software Organization in Chile, Dr. Marcela Cruchaga, academic at the Mechanical Engineering Department of the University of Santiago de Chile, Dr. Mohamed Ezzeldin, Assistant Professor at the Department of Civil Engineering of the McMaster University in Canada, and finally, Dr. Juan Pina, Assistant Professor at the Civil Engineering Department of the University of Santiago de Chile, who is also the Director of this International School of Perspectives on Seismic Hazard Analysis and Disaster Risk Management, as well as the moderator of this event. Finally, I would like to remind you that this seminar takes place on Zoom webinar, which means that we are only projecting the panelist screens and not the participant screens. But you can send your questions throughout the whole conference in this question and answers box. And they will be answered by the panelists directly in this box or live in the second part of the event. Now, without further ado, I shall give the floor to the moderator, Juan Carlos.
So welcome everybody to this webinar. It's a pleasure to have you here and that you could join us for this chat that we're going to have today. The goal behind this talk is to discuss some issues related to earthquake engineering, resilient infrastructures, and the motivation behind this is, well, it tracks back a bit to February 27 in 2010, when Chile suffered one of the most destructive earthquakes recorded in history. When you ever come to Chile and ask people about that, people that was here, they tell you experiences that sometimes are taken out of a movie, for how hard that was and how the impact that had in their lives. And that's similar, or events like that has happened elsewhere in other countries like Japan, USA, Indonesia, to just name a few. And then these high magnitude earthquakes have been happening or recorded since 1900. And these kind of events have challenged and drive engineers worldwide due to the ongoing search and demand for safer and more resilient infrastructures. Procedures for the analysis and the design of seismic resistant buildings and bridges exist in the world since earlier 1920 or something like that. And because engineering is something that's a living science that evolves all the time, constantly looking for better design methods, standards, and procedures, we are always, as engineers and researchers in the topic, looking for how we can find better methods, use computer methods in a better way to aid our design and analysis process. And this is particularly relevant when we are talking of seismic hazards, for instance. So some of the innovation and practices for the analysis and design of resilient structural systems are related nowadays to using computer-aided design. And this is one of the topics that will be discussed today. First, we will have Aníbal Graterol from ESSS, and he will discuss the power of numerical simulations as a tool to study the complex nonlinear response of structures subjected to earthquake conditions. Some of the topics he will discuss will be about the use of finite element-based nonlinear modeling, analyzing time domain seismic analysis, and fail-safe structures. After Aníbal, we will give the floor to Marcela Cruchaga from SACH, from the Department of Mechanical Engineering. And she will tell us, or she will discuss with us her experience in modeling something that is very relevant nowadays, particularly in a country where Chile, because earthquakes always, or many, unfortunately, many times come coupled with tsunamis. So she will talk to us the use of some numerical tools to study the important multi-physics fluid structure interaction events that take place when tsunami struck Earth, land, and the buildings and constructions related to it. And finally, we will have Dr. Mohamed Ezzeldin. He's from McMaster University, as Margarita already mentioned, and he will look into seismic level performance quantification of reinforced concrete block shear wall buildings applied to some nuclear facilities in Canada. That's the work he's carrying out currently in McMaster. There, I think it's related to experimental and numerical work, and also an interesting topic he will touch upon is the interaction between these two words, experimental and numerical, via seismic hybrid simulations. So without further ado, I will give the floor to Aníbal so that he can start going through his presentation.
Perfect. Thank you, Juan Carlos. I will start sharing my screen. Please confirm me if you can already see my screen.
Yes, Aníbal.
Oh, okay, perfect. Okay, well, hello everyone. I'm Aníbal Graterol, and thank you for joining us today. I have the pleasure of presenting this interesting topic about finite element analysis of a structure under seismic conditions. I will focus on non-traditional models, that advanced model that could include severe nonlinear response due, for example, to a severe seismic event. Let me start with a very brief introduction about myself and the company I work for. I'm a mechanical engineer. I work for ESSS as a simulation specialist and technical coordinator. We are a company that works as premium channel partner of ANSYS. This is a very well-known company in simulations. We even developed software, for example, RocketM, that is well known in the mining industry. Okay, well, let's see what are the contents that we are going to talk about in this opportunity. As I said, I will talk about finite element analysis applied to nonlinear seismic response. In this context, we will present how this linear behavior is defined, what does we mean with advanced nonlinear analysis, how to deal with nonlinearities in a time domain analysis, and finally, we will present some ideas about how to evaluate fail-safe structures and sacrificial components, and how simulation could help us to understand the behavior of this kind of components. Okay, well, what is this all about? Well, nonlinear behavior refers to a nonlinear relationship between the applied forces and the obtained displacement. In this case, the stiffness of the structure is not constant, and it changes during the deformation. This behavior is associated with, for example, nonlinear material response as metal plasticity, and in this case, we have a nonlinear relationship between strain and stresses. But even if we have a nonlinear material response, we could have a nonlinear response of the structure itself. For example, if large deflections occurs or large rotations of the different components of our structure. Also, if we have different components that could touch themselves during a load condition, producing a change on the contact statics, this will be reflected as a nonlinear response. We could expect one or more of these source of nonlinearities during a seismic event, especially if we are facing a severe seismic event. To handle a nonlinear analysis associated with a dynamic response, we need to use a time domain analysis. Of course, nonlinearities and dynamic response could require an important computational effort and could include a challenging mechanical response. From a numerical point of view, we can handle this condition using an implicit method, for example, the Newmark method, or an explicit method. On the left hand, let's start with the implicit method. This is an interesting approach. It's a very traditional method, but it requires an iterative process for each time step in order to capture the nonlinear behavior of the structure. The benefit of this approach is that it is always stable and there is no stability condition to comply with. But if it could be difficult and sometimes very, very difficult to obtain convergence in this iterative process if complex nonlinearities are present. On the other hand, on the right side of the screen is the explicit method. This one has the advantage that doesn't require an iterative process when nonlinear behavior is present, which is a great advantage. But we need to comply with a stability condition that relates time step with mesh size. Usually, this method requires very short time steps to comply with the stability, which imply that only short duration effects are normally studied. With what is a short duration effect? It could be, for example, 1 second, 2 seconds. That could be considered as maybe long study when we use an explicit analysis. But if we are facing really challenging nonlinear behavior, most of the time, this is the required method, because it could be not possible to achieve convergence if we use the implicit method. The examples that I will show in the next slides were performed using this explicit method. It's a very interesting one. Well, which are these challenging situations? If we are facing a severe seismic event, we could predict that buckling will occur. Also, we could face very complex material behavior, including softening and material failure, and even impact loads. In this kind of situation, it is important to consider fail-safe and sacrificial components. For example, about sacrificial components, we have the image on the left side. We could think, for example, of a shear key of a bridge, which is a component that is required to fail once certain load is reached. If under a severe seismic condition, this component doesn't fail, it will compromise the main element of the bridge. This is not what we want in this condition. So we need to assure that these kind of components will fail under certain conditions. On the other hand, for example, we have bolted connections. In this situation, maybe we could handle some kind of failure as plastic strain, even important component deformation. But we don't want a complete failure of the joint, of the bolted joint, as it is shown on the image. That is what we want to avoid. For this situation, it is very important to determine the maximum force that a component or a structure could resist. And we need to determine that maximum force. For this situation, it's important to understand how is the buckling behavior of a structure or even a component of a structure. In understanding this case of buckling, in this case, we have a nonlinear response that involves an unstable condition. This means that suddenly the structure is not able to handle the applied loads, as we can see on the image on the right side. If we want to verify what happens after the unstable condition is reached, we need a special numerical approach, like the explicit method that we mentioned before. This way we can achieve to perform analysis that this one that is shown on the screen at this moment. About material behavior, let me go one slide after this one. Everything that is associated with phenomena like, for example, softening a material failure could be difficult to handle, but it is possible to be analyzed using numerical simulation. In the particular case of softening, this refers to a decrease in the material resistance once a certain stress condition is reached. Even an implicit approach could handle this kind of behavior, but the use of explicit analysis will be very useful for these complex situations. Once again, we have on the screen the case of a shear key. This is a real study that is being performed by the Universidad Católica, and in this situation, the maximal load of the shear key is being calculated using simulation, specifically in this case with ANSYS LS-DYNA. All of the nonlinear behavior of reinforced concrete, considering material softening, it's being applied in this research with very good results. If we are talking about ductile metals, another challenge could arise. Usually the maximum plastic strain is used as a failure condition, but the maximum plastic strain that a metal can handle depends on the triaxiality condition, which is a relationship between the hydrostatic stress that is shown on the, it's below on the image, and the equivalent stress. Nowadays, on advanced finite element analysis tool, we can handle this kind of failure condition as a material behavior input. This could be our input to define what will be the condition for the failure of the material. It's a very interesting capability. For example, let's see this case. This is the analysis of a bolted connection. We are using this approach of considering the maximum plastic strain that the material can handle based on the load condition. You can see on different simulations and different even test results, and you can see that we have a very good relation. We have close results, a very good similarity between the test results and the simulated results. We are capturing the behavior of the material under different load conditions. Okay, how this failure is modeled on finite element analysis. We have two main approaches. One of them is the erosion approach, and the particle models approach. With the erosion approach, an element is deleted from the simulation once a specific mechanical condition is reached, for example, maximum plastic strain. But what is the problem with this approach? If we delete an element, we are losing mass and energy from the analysis. It's a good methodology. It could show us good results, but we need a very detailed mesh to achieve these good results. Another interesting approach is the use of particle models. In this case, for the modeling of a continuous material, we use particles that are bound together. In this case, the failure is modeled as the failure of a bond, but not the failure of a particle. In this way, the mass and the energy that is being calculated on the simulation could be conserved. To finish the presentation, I want to show you these cases of impact analysis. In the right side, we can see an impact over a metal part. This part is made from different components, from multiple components, and you can see that the contacts between that components fail under the load conditions. This could be, for example, an illustration of an event that could occur on seismic conditions. On the left side of the screen, you can see an impact over a reinforced concrete beam. In this case, you can see that there is some damage on the materials, and that damage is being calculated by the simulation. Of course, in simulations like this, material damage and bond failure will have an important effect on the maximum load that this part could resist, and the simulation represents a valuable tool to determine what the maximum forces that structures and their components can resist. Well, that's all for my part at this moment. If you have any question about these topics, it will be really nice to talk to you on the question and answer section. I will pass the screen.
Thank you very much, Aníbal, for your very nice presentation. I would like to remind the audience that if you already have some questions, you can put them through to the chat so that we can pick them up and we will discuss them after all the presentations are finished on the Q&A session. Now I will give the floor to Dr. Marcela Cruchaga from the Mechanical Engineering Department of ESSSS, who will talk about fluid structure interaction and tsunamis. Marcela?
Yes, I am here. I will share the. Okay. Okay. Thank you, Juan Carlos, and thanks the audience to be there. Well, the work. Let me see if you are just. Let me. Okay. Wait. Are you? Wait. Like this. Okay. Well, now I am ready. Okay, thank you again. And well, the work I am presenting is the fluid structure interaction analysis under tsunami effects. And the main idea is to determine forces on buildings and the forces due to the tsunami waves in a realistic condition. This presentation is based on the work previously published by my colleagues, together with my colleagues from other universities in Chile, the Universidad Católica de Concepción, la Universidad de La Serena, and colleagues from Mexico. Well, as I told you, we took as a case of study the tsunami event during September 2015 in Coquimbo. Coquimbo is a city near La Serena, just here, around 500 kilometers to the north of Santiago de Chile. And as you can see here, this picture is really, this image is, you can have an idea of the devastation in the region and how the tsunami affects the life of people. Really, unfortunately, it's very difficult to predict the occurrence of a tsunami. And normally you can detect the tsunami and there are only very few minutes for evacuating. It is these reasons made of important the determination of the evacuation zones or the evacuation areas, and to have the ability to design tsunami shelters and evacuation paths, and all of them requires the structural design of buildings and other coastal structures. Within this context, to construct a building or to construct all other coastal structure, to design other coastal structure, you need to define the forces acting on these structures. Well, normally, you have some guidelines or norms that describe what you need to do to build or to design a building. Here in Chile exists the norm that is telling here, this norm from 2015 and 2016. And as his name tells us, is the norm for structural design building in risk area of flooding due to tsunami or siege. Well, the main thing you need to define normally is the methodology used to estimate different tsunami loads, including hydrostatic forces, aerodynamic forces, buoyancy forces, impact forces due to waves or debris. Well, you can define these forces taking an average value of the flood. That means you can take average value for the velocity, for the pressures, or for many flow parameters, and you can apply some rules, some equations, and to define these forces in average. But if you do that through the computational fluid dynamics, you can include high resolution, the 3D effects, the strong time dependence analysis, and more complex topology and bathymetry. And it is why we perform the analysis using computational fluid dynamics in this presentation. All the requirements are high computational resources, formulations, numerical modeling, machine to run the cases, man hour, the working man hours, or the human capital you need to run and to perform the models, and the technology. Many things are needed to solve problems in this area and many other areas too, and to represent more realistic conditions. Well, here we are. This is the risk zone. This pink zone. This pink zone is the risk zone in the area of La Serena and Coquimbo, and this is the inundation hazard map that you can collect from the web page of the Hydrographic and Oceanographic Service of the Chilean Navy. And as you can see, you have shown that more than 1 kilometer from the coast inside the land, and this zone need to be evacuated during the tsunami warning. It's very difficult to move people from this zone, and also in the condition of very alert, is a very strong alert condition. Well, Normally, really, we have the fortune that the Pacific Tsunami Warning Center and the Center for Hydrographic and Oceanographic Service of the Chilean Navy, normally they can give us the warning message. But the problem is to evacuate on time, and what you cannot control is the damage. The damage cannot be prevented. And it is really a problem, and you need to build things that try to avoid the very high damage in this type of event. Okay, well, what we need to do is to define the zone, the region that we want to analyze. In this case, we define a region in this zone is Coquimbo here, and we define this area in the red rectangular. But under what conditions we define this model? First, we have the reference model. The reference model is a model based on nonlinear shallow water equations, and from this model, all the hydrodynamics variables are computed. We need to know the velocity of the tsunami, the flow velocity, the amplitude of the waves, the flow direction, and this is not reported, and it is normally not recorded during the event. It is also a problem. Hence, we will take some details to define the area to model based on another numerical model, okay? This reference model is coming from the nonlinear shallow water equations, but this original model gives us from some data coming from the tsunami waves that you can register far from the coast, near 300 kilometers from the coast. In the dark void, you can take some information from the velocity and normally from the water level, the sea water level during tsunami, and after that you can propagate the wave to from the sea, from the open sea to the land, to the coast. And you do that, and we do that with a nonlinear shallow water model. From this, we can define near the coast the level of the water, the velocity, and the direction of the velocity. With this, we define a domain parallel to the tsunami flow direction, and we took this dimension for, in this case, 100 meters and 300 meters, near to these special topographic things. We have the railway here and buildings near the coast. And these points in green are points that we compare the shallow water model with the model we expect to run using in this case, computer fluid dynamics using the smooth particle hydrodynamic techniques that provide 3D equations, the solution for 3D equations of the Navier-Stokes equation of the flow. And we use high resolution in topography and morphology of the beach, just in this region. Include the buildings, the beach, obviously, the buildings, and the railway, and compute the tsunami hydrodynamics variables and forces on the buildings. Well, with this, before do that, I want to show you this. I don't know if it is not running. It's a pity. I couldn't. Let me see. Let me see. Okay, now. Well, it is really fantastic to demonstrate some capabilities of the formulation in this case. But really, if you see this movie, it is not realistic. You have tsunami waves higher or at least equal to the tallest building, And also it is promoted for a wall that push the water to the buildings. These are fantastic and could give us some idea of the capabilities, and also can serve as a basis for a movie. But really, we need to define certain aspects of the model more realistically. Well, topography is one, and the boundary condition, how to impose the motion of the water, is also a topic, a relevant topic, and is also a topic on discussion. Well, what we assume first is that we have some points, the monitoring points here, that we can measure velocity and water depth, and with these two values we can determine the flow rate. But we impose this flow rate coming from realistic conditions using the motion of a piston. This is a reservoir with water. The piston moves from down to up, and with this model we generate the tsunami wave. The second aspect is that we have in the registers from the wave of the tsunami in 2015, we can obtain large waves, but we can distinguish 5 waves. The main waves that occur during the event were 5, regular 5, 35 minutes apart one from other, and we took as a reference the second wave to model the flow rate for this simulation. We tried to reproduce this wave, measure in quantity of flow rate, and promote and run the simulation using this condition. Well, we assume 3 different models. One is practically the same as in the reference ones that run in shallow water. These have not the buildings and have not the railway. The second one, B, have only the buildings, and the model C have the railway. And we will compare the differences in the velocities and the forces. Here we have the flow velocity. In which points? In points near here, okay, and also over there. But we can see here the blue one is near this building, and we can observe the wave that advances to the land. But we need to think that we have a maximum velocity of the flow velocity of 2.5 meters per second. If you think that you as a human, you can walk normally 5 kilometers or 5 or 4 kilometers per hour, you normally have me or you have a walking speed of 1.2 or 1.4 meters per second. But you need to move more quickly to avoid this wave, the tsunami wave. And you need to run probably, or you need to walk in paths like this, and probably during night. It is not easy. It is very difficult to evacuate places like this, places that are flat places, and you need to move faster than you used to move. Well, finally, we have some results on forces, and in this case, the model C with the railway have forces around 10, 15 or 20% greater than the model without the railway. Well, Finally, as a concluding remark, I want to conclude that the SPH model built under consideration of real data. It was built using dual physics, and it was run in the machine, in the Abacus machine in Mexico. All this work was done in the context of a project, a CITED project called CADIN. We tried to define appropriate boundary conditions, also appropriate hydrodynamic behavior of the tsunami, a better representation of the flow, including the buildings. Also the topography and bathymetry was also included. Well, and this work can show you at least the main details you need to take into account to define a realistic model of this type of problems. And it is only for 100 meters of coast. If you need to analyze it for a very big coast, the problem is obviously biggest. Well, I really thank your attention. I thank the Fondesit that helped me to do this work in the context of the project. The maps and the photos that I present are in the public press and media, like indicated here. Well, thank you very much for your attention and all the questions. I will be nice to answer your question in the session of questions. Thank you very much for your attention.
Thank you very much, Marcela, for your very nice presentation and your very, very nice results of the modeling of tsunami. I don't know whether they are nice or they are scary, but okay, we'll leave that for later. But anyway, very, very nice work. Now, I would like also to remind the audience that they can keep on posting their questions in the chat. We will go over them afterwards. And finally, we are going to go through the presentation of Mohamed. As Margarita mentioned earlier, he's an assistant professor at the University of McMaster in Canada. So Mohamed, the floor is yours. So you can start your presentation.
Thank you so much, Juan, for the presentation. And I really enjoyed the last two presentations. They are really valuable. So talking about hazards, like I'm very interested today. Let me first share my screen. Perfect. Okay. So today I will talk about like the system level performance of concrete structures, and I would like also to show you a case study that we have conducted at McMaster University as well, to show you when you test a building, what's the difference between testing a building and testing components as well individually within a building. So I would like to start with the agenda first. So how did I identify research directions and knowledge gaps, and what's the status of the reinforced concrete systems as well in Canada? And I would like to show you a case study of a multi-phase research program that has been conducted at McMaster University. It had 4 research phases, and I would like to discuss with you like the 4th research phase through an experimental system level study, and also what are the current research projects that are currently at McMaster University as well. So before I talk about reinforced concrete, I would like to let you know like how did I identify and how did I get there. So I was very interested to identify research directions and knowledge gaps for future research opportunities. So my question was, what's the structural engineering research community worldwide doing in the past 26 years at that time, for sure, at 2016. So for that reason, I did text mining analytics on more than 11,000 papers using two big journals, Journal of Structural Engineering and Elsevier Engineering Structures. And I have selected these two journals because they are very they are very broad in their objectives over all other journals, and they are also top tier in the field. So as you can see from the slide, like I developed a topic interlinkage network for all the topics. So basically I quantify how many papers between each two topic, or you can quantify the strength between two topics. So for example, let's take an example. So for example, you can see that earthquake engineering or seismic engineering, topic number 1 in the very right, is highly linked to the nonlinear modeling through a large number of published papers. When, for example, compared to those papers between topic 1, which is the earthquake engineering, and fire testing per se. So by doing so, you can identify what are the knowledge gaps in structural engineering, and how many papers did we publish between earthquake engineering and nonlinear modeling relative to earthquake engineering and fire testing as well. So this was worldwide analysis. But let's go back to Canada and look over the database of NSERC. So NSERC basically is the funding agency for all the grants and awards for research institutions in McMaster. It stands for National Science Engineering Research Council. So if you look over the past 29 years at their database to identify funding opportunities, you can see, according to the numbers in the database, like concrete structures are really allocated large amount of money when compared to other materials like steel per se. But if you have a closer look, you can see that like concrete structures also can be included in structural engineering or earthquake engineering from the pie chart that you can see. So you know what, I decided like to download the entire database, like all the abstracts, all the research and awards that have been awarded in the last 29 years by NSERC. And you can see, of course, within the structural engineering, and also did some text mining. And I came up with very interesting result that 25%, around $20 million, which is 25% of the NSERC funding for structural engineering in the past 29 years in Canada were dedicated to concrete structures. So this is large amount of money. However, when you look at the reinforced concrete systems in Canada, this makes lots of sense that can address why NSERC spends so much money on concrete structures. These systems comprise many infrastructure systems in Canada, like nuclear power plants, power networks, transportation networks or transportation structures. And because of the aging infrastructure, or because the ongoing changes in the building codes and design standards due to the continuous changes in the seismic demands, sooner or later, we need to rehabilitate many reinforced concrete systems, and this needs more than $70 billion for rehabilitation. Also, squat concrete shear walls, they are all over the place, not only in Canada, but worldwide as well. They can be in many low-rise buildings. They are also in many nuclear power plants in Canada. If you really look at the literature, you will see that like squat walls are one of the most understudied system in the literature at the system level. And this links with my research and my presentation today, that some key system level aspects, for example, twist, ultimate strength, cannot be evaluated through component level studies. You have to do system level studies to identify those key system level aspects. Now we appreciate the importance of such systems and the system level studies. Over the next couple of slides, I am very interested to show you another similar reinforced concrete block building that McMaster focused in the last 5-6 years within a multi-phase research program. So before I start with my focus, I'm trying to compare component and systems, so walls with building. So the research is in the 4th phase of a multi-phase research program that started by testing individual components in the loading direction, so wall 1, 2, 5, 8, and another building system with the slotted slabs, as you can see from the top right, to minimize the coupling between these walls in phase 2. So to consider only the in-plane rigidity of the diaphragm or the slab. In phase 3, Another building system similar to that in phase 2, but this time without slots in the slabs. And this building was tested to consider the in-plane and the out-of-plane rigidity of the diaphragm or the slab. And in phase 4, we tested a similar building, but to facilitate a direct comparison between phase 3 and phase 4, we replaced all the walls in the loading direction with walls with boundary elements to consider or to quantify the enhancement in the resilient performance of such system. So if you are not familiar with walls with boundary elements, let's talk about first the difference between reinforced concrete and reinforced concrete block. So to start with, reinforced concrete walls on the left or in the left typically have closed horizontal stirrups and 2 layers of vertical reinforcement. This is in reinforced concrete. However, in reinforced concrete block walls in the right side typically have single leg of horizontal reinforcement and a single layer of vertical reinforcement as well, due to the practical limitations associated with the block configuration. So you cannot add many layers or add double layers of vertical or horizontal reinforcement. However, when boundary elements are used, boundary elements allow close ties to be used and allows also multiple layers of vertical bars to be used, and this delays the buckling of the vertical reinforcement and also enhance the overall seismic performance of such systems. However, this system is relatively new, and as such, like the relevant design standards and national building codes like the MBCC, National Building Code of Canada, and the CSA S304 have not yet assigned any seismic performance factor for such system, and they recommended that more studies are needed to come up or to develop a unique seismic performance factor for such system. So the question here, and we needed to answer, can we design such walls with the unique seismic performance factor given their enhanced performance than those traditional walls with rectangular cross section? So for that reason, we used the FEMA P695 methodology. And if you are not familiar with the FEMA P695 methodology, it evaluates the seismic performance for any seismic force resisting system, steel, concrete, masonry, by performing nonlinear analysis and also by evaluating the collapse margin ratio against the maximum considered earthquake or against earthquakes. However, as you can see from that figure, this methodology needs a nonlinear model. So for that reason, we developed an OpenSeas model. It's an open source or an open software through displacement-based beam column elements. And then we also, for the confined grout in the boundary elements area, we also assign different material properties to consider their higher strain capacities than those outside the boundary element. So those in the boundary element area, we identified or we assigned them different material properties. And we used that model and we validated that model against the experimental results that are available at that time. And as you can see from the two figures, that the model is in a way able to simulate the performance of, or the characteristic of cyclic performance of the walls, including stiffness degradation, strength degradation, as well as the pinching behavior at different drift levels. So using that model, using that OpenSeas model, we redesigned two walls according to the NIST, which is the National Institute of Standards and Technology, identified that two walls, they evaluated 20 walls, but I'm showing here only two walls. They mentioned that two walls, S1 and S2, which are walls without boundary elements, just rectangular cross section, failed and didn't meet the acceptance criteria of the methodology. So the question was, can we design or redesign those walls using boundary elements and evaluate their performance against the FEMA P695 acceptance criteria? So we use that OpenSeas model, redesign those walls, and then we performed incremental dynamic analysis or nonlinear analysis. And as you can see from the figures, that there was an enhancement in the performance of the walls when boundary elements were used. Instead of having collapse a median intensity of 0.84 G, we have now like 3.17 G when boundary elements are used, and so on. So as you can see, when we develop collapse fragility curves, the such system can enhance the seismic performance and can be really provided a higher R factor. And if you're not familiar with the R factor, like it's the factor that can reduce the seismic forces to account for the inelastic deformation. And as you can see from the table in the bottom, that the two walls that designed with boundary elements were able to meet the acceptance criteria of the FEMA P695 methodology. So given that we now trust that system and it can enhance the seismic resilience of reinforced concrete block walls, we wanted to make sure that, how about like if we tested that building at the system level, if we tested a full structure or a full building at the lab, and then as I mentioned, like in phase 1, we tested individual components. We put those individual components in a building with the slotted slabs to consider just the in-plane, and then another building in phase 3 without slotted slabs to consider the in-plane and out-plane rigidity of the diaphragm. And then we replaced all the walls in the in-plane direction or in the loading direction with walls with boundary elements. So we tested the building in phase 4 with boundary elements using a hydraulic main actuator. We tested that building under reversed cyclic loading from the second floor to represent seismic forces or seismic demands. And the effect of the actuator on the out-of-plane rotation of the slab was minimized using a secondary vertical actuator to carry the self-weight of that main actuator. And also during the test, we collected lots of data and we used lots of string and displacement potentiometers. We measured the sliding, we measured the uplift and the curvature of all the walls as well. We are interested to measure also the building lateral displacements in all directions. So we can see that we have displacement or string potentiometers in the two directions. Also to quantify the expected building twist as the building center of rigidity wasn't coincide with the center of the mass. So when we tested that building and we compare that building with the building in phase 3 and the components in phase 1 and the building in phase 2 as well, as you can see that the ultimate stress of the building or the systems in phase 3 or even phase 4 are 50% higher than that of building 2 with a slot slab. So when you test two components only, or if and you sum the strength of that components, or we test that components within a slotted slabs building, consider only the in-plane, you can see that that the building in phase 3 and 4 with rigid slab achieved higher strength. However, although the CSA and the TMS, the current standards for masonry structures in the United States and Canada, ignore slab coupling. However, as you can see from this figure, that there is a significant influence of the slab coupling on the system level behavior, and this cannot be quantified through component level studies because these walls tested did not respond at cantilevers within a building, and therefore the overall lateral load capacity of these buildings were increased when you consider the slab coupling. So given the importance of the system level tests, like our plan now at McMaster, the current research project that we are now working on at McMaster. So the first one, we are interested to test or evaluate complete reinforced concrete systems, given the importance of system level studies, to assess their nonlinear response under complex loading condition, either using shake table, our shake table at the ADL, or using reversed cyclic loading. Under complex loading conditions of shear, moment, axial load, and torsion as well. And the question here is, how adequate are the current design standards in Canada? For example, the CSA 823.3, which is the design standard for concrete structures in Canada. How adequate is the design or the seismic design provisions in that standard, or any other relevant standards, considering the system level behavior? Also, the second research project is related to squat walls in nuclear power plants. Although most of nuclear power plants in Canada and worldwide rely on reinforced or squat reinforced concrete walls as their primary seismic force resisting system, the current relevant standards, the CSA 289 and the corresponding the corresponding design standards in the USA as well, ACI, does not have specific design provisions for such walls and completely relies on concrete design standards for buildings. And the question, what's the adequacy of current seismic performance factors and provisions assigned to massive squat walls in nuclear power plants and other containment structures. We are now developing a seismic hybrid simulation framework at McMaster University for testing reinforced concrete systems. So the basic idea, if you are not familiar with seismic hybrid simulation, you test the portion that has uncertain nonlinear behavior physically at the lab, and then the remainder of the system is numerically simulated using any numerical software, for example, OpenSeas. So we can use such hybrid simulation results to evaluate, for example, squat reinforced concrete shear walls in nuclear power plants without the need to recreate the very large mass associated with the rest of the building. So we can do that in the model. So basically, you have a model, and then you apply a ground motion or a step of ground motion to that model, as you can see from the top left, and then getting the displacement of that portion that you are testing at the lab to open Fresco or a test PC or any other software that can speak to the servo controller of the actuator at the lab. Getting that displacement to the lab, calculate the force, or getting the force from the lab back through the same path to the model for the next ground motion. So basically, you are testing one wall or one uncertain or nonlinear component using the hybrid simulation to get the system level performance of the building. Also, the next project that we are interested right now at McMaster as well, and myself, that given the large volumes of the experimental data that are currently available, it's about time to use emerging areas like artificial intelligence, like genetic programming and machine learning techniques in structural engineering applications. I see that these emerging areas or emerging computational techniques will be able to predict several aspects of structural engineering applications of complex nature that cannot be developed or evaluated using physical phenomena. So that we can develop data-driven models using those data sets. And for sure, you have to gain or to assess those equations by your structural engineering sense. So we already started with a database of 256 squat reinforced concrete shear walls with boundary elements to come up with a predictive equation for nuclear structures. And as you can see from the figure, that the current ESSS 43 cannot that much predict their ultimate strength. However, when we use genetic programming, we came up with an equation that can predict in a very high accuracy the lateral strength of such walls in nuclear power plants. So given that, as a one technique, which is the genetic programming, I believe that such emerging areas can facilitate a lot of tools that can facilitate our understanding to evaluate the seismic resilience of many infrastructure systems. At that point, I'd like to thank you. Thank you for attending today. Thank you for McMaster University and ESSS as well for the funding. And I would like to return the floor to Juan. And I'm very happy also to answer your questions.
Thank you very much, Mohamed, for your presentation. It was very nice, very interesting work, and very interesting the point of hybrid simulation that you are starting to carry out. Now we are going to start a bit with the Q&A sessions. I have some questions that has been already posted in the chat. I suggest we start going over those questions first. Probably we can start with Aníbal. There are some questions there that he can help us at. Rodrigo Fuentes is asking about what is the principal complexity of using the particle or SPH simulations method. Aníbal?
Excuse me, Juan, could you repeat that? I had some problem with my audio.
Okay, yeah, no, I suggest that we start going through the questions that we are in the Q&A session.
Yep.
The first one is from Rodrigo Fuentes. And he is asking about the complexity or the principal complexity of using the particle-based method for simulations. So can you give us some feedback on that?
Yeah, well, these kind of simulations are more computational expensive. So usually we need to divide the geometries and use a traditional finite element analysis on most of the geometry. And on that region, when we expect material failure, use, for example, SPH or SPG method. There is another one that is called peridynamics that is used for brittle materials. Very, very interesting. And also, we usually need to calibrate the material properties when we use this kind of formulation. So we expect to have experimental results on some kind of test and replicate that condition with numerical analysis. We need so to implement an iterative process in order to achieve a good accuracy on the results. After we have accomplished this stage, we can use the simulation for a different condition that was not previously tested with experience.
Okay, nice answer. Also another question now from Rodrigo Tapia, that I know probably Aníbal or also Mohamed can give a hand on that. He says, for the study of large structures such as buildings, it's possible to use explicit methods, and asking about what is your experience using that kind of method to solve this modeling the nonlinear response under dynamic conditions of buildings and structures such those ones.
Okay, well, for example, in my experience, if we are talking about explicit dynamics, as I mentioned during the presentation, we are talking usually about very short phenomena, 1 second, 2 seconds. Also, we are talking about very expensive computational studies. So it could be useful to evaluate a very complex structure. That could be possible, but it could be useful to focus on that part of the structures where we expect a very complex nonlinear behavior, such as material failure, softening, post-buckling, that kind of things. On the other part of the structure, we could use the to understand the macro behavior of the structure. It is better to use an implicit method. We could even analyze a larger duration phenomenon with this kind of formulation.
Thank you very much. I don't know, Mohamed, what is your experience on that kind of thing using software such as OpenSys?
Yes, so as you know, like OpenSys is an open source, so you can model different systems. But like again, back to Aníbal, like it's simplicity versus accuracy. So you can you can do like a very complex model, but it's not accurate. However, you can do like a very simple model that can be very accurate relative to that complex model. So as Aníbal mentioned, like you have to check like where is the non-linearity that you are expecting. For example, in hybrid simulation, when we model like a wall within a building, we can model that wall or we can simulate that wall like in the lab, like the first floor, because we are expecting that second and third and fourth floor under seismic loading to remain elastic. We can model that part using elastic elements to make it not computationally expensive. However, that first floor can be modeled using displacement-based beam column element or force-based beam element, or even tested at the lab using hybrid simulation. So it's again like it's simplicity versus accuracy, and micro models versus macro models. So I would say that the parts that you are expecting high nonlinearity and you are interested to check, I would go with the micro model. But as you can see from the model that I showed, that was a macro model for reinforced concrete block shear walls.
Yes, thank you very much. Yes, when you start looking into problems with big buildings and such, the models become heavy, complex, and when dynamics analysis require this scales up a bit. Yes, going for the next question. This is directed to Marcela.
Yes.
I
Well,
don't know if you
directly not. Well, that's right. What the people say, Sergio told us that the second, third, or the follow, if you have other waves, normally you have debris, but not. It was not considered in the modeling. This type of things. No, not in this model. Not in this model. Could be taken into account. Yes, but it is also very difficult to assess if they are well considered or not. But not in this case, directly not. It was based on a flow dynamics and based on in the topography and bathymetry, the real bathymetry and topography of the zone, of the region analyzed, but not in the debris actions.
And how complex would be that to incorporate that kind of phenomena?
Well, probably really. I know many simulations that attempt to solve this problem, and it's a tool that we can use or what we can develop, but it is up to now is very high computational cost, a lot of time and of analysis, and up to now it's very difficult to take it into account. I know many computations that take into account this type of things, but I cannot say if they're really realistic. And computational, and the computational time is very long time, and it's a very long time analysis. Itself is a very long time analysis. If you add all these difficulties, a very big problem. Not easy to solve.
Okay. Yeah, thank you very much for your answer. It's clear that it's a very complex, and well, talking about large scale problems, that's one of those that it's very large and complex with a lot of parameters. And I think we have another one, a question for Aníbal about recommendation of a software for modeling accurate failure of materials and stuff like that. Which software would you recommend? Which approach would you recommend? Nonlinearity, damage, SPH? I don't know.
Yeah,
I guess that it goes that direction.
Yeah, I think I would prefer to recommend maybe the approach, the explicit. I think that explicit dynamics is the best option for this kind of modeling, because we will deal with really complex nonlinearities. So I recommend to look for a software that has this kind of capabilities. Also, we need to understand the failure model that represents in a proper way our material, and be sure that that software can capture this failure model that we need to replicate. So I think it's not responsible for me to mention what's the best software for this kind of simulation, but that's like the key aspect that should be investigated previous the acquisition of any software.
Okay. Thank you very much. Yes.
So I would like also to add, like right now, like researchers are moving towards hybrid models, not like hybrid simulation tests, but hybrid models that, as I mentioned in the presentation, you can do like hybrid models by testing a component in the lab and also doing a numerical model for the remainder. But like there is also hybrid models between the different software packages. So you can model a wall using, for example, Abacus or ANSYS, for the first floor if you are really interested to do micro model, and then you can connect the other 2 or 3 or 4 floors above the first floor using, for example, a macro model using OpenSeas. So you can connect different software packages or different like modeling techniques within a hybrid model, because people like might think that hybrid means like physical or test and a numerical model. No, you can connect or you can link different modeling techniques within a hybrid model as well.
Okay, nice. And going on that direction, and considering your experience in hybrid modeling, and how complex is that, and how big the simulations are taken, and how you have to manage interaction between your, for instance, your test setup and your models? How complex is that to get that moving, and how large the simulations tend to be, or the process? Can you talk us a bit more in details about that?
Yeah, we just like as I mentioned, like we just started like 6 months ago, like to develop the hybrid simulation framework. We didn't test yet like a component, but we are in the process of developing the framework first. We are interested to test like stiff walls, like those walls in nuclear power plants. They are very rigid. So those walls are very tricky, because like any errors in the displacements, because they are very stiff, you will have a very large difference in the forces as well, because any like different in displacements, if you have a high stiff structure like those massive squat walls, you will have instability in the hybrid simulation framework as well. So we have to get like special sensors. So right now we are doing like some rehearsals or some tests on steel beams or steel columns, just to make sure that the hybrid simulation framework is working, and the servo controller or the experimental actuators can talk to the OpenSeas model, and the OpenSeas model can talk back to the experimental actuator without having any instability. I know it will take time, but we are in the process of conducting the first test at McMaster as well.
Okay, nice. Yeah, that's a very, very interesting topic, I think. It's nice to have a complete circle between connecting the experimental and numerical world.
Yeah, and one of the advantages also, like it can also we can link our research to other universities, not only in Canada or in the United States, but also other universities, because like you can do a hybrid simulation between different universities using their labs. For example, you can test one column at McMaster and one column at other university, Chile, and then you can do like a numerical model in another university, for example, in the United States. So you can use the physical space at the labs of different universities within one test or within one building.
Yeah, so it opens the door also to a different scope of collaboration between researchers worldwide.
Yep.
That's also, I think,
yes,
it's a very
but like
powerful.
The first step, like to develop the framework at McMaster first.
Yeah, I can imagine. Yes. Well, I think. Okay, thank you very much, everybody, for your presence here. I would like to also thank Marcela, Mohamed, and Aníbal for their very good, nice presentations. Before giving the floor back to Margarita, I would like to talk about the upcoming International School on Seismic Hazard Analysis and Disaster Risk that it will be held at USACH somewhere next year, and everybody interested can contact us. We will be posting information related to that in our traditional online channels, and they are all invited to participate. You will hear from us, and it would be very nice to have people coming from everywhere to Chile to visit us, and this is available. Thank you very much. I will give now the word to Margarita.
Thank you.
Yep.
Thank you.
Yes, I would also like to thank you very much, everyone, all the speakers and the moderator, for your time and your great presentations. We invite you to the International School next year, as Juan Carlos said, and thank you very much for coming, everyone.
Thank you, Margarita.
Thank you so much. Thank you.
Have a great
Thank you so much,
evening.
Margarita.
Goodbye.
Bye.
Well,
Bye.
bye.
Thank you,
See you.
everybody. Bye-bye.